basically, I want to show you this to explain you what are we looking for and what are the things that we have to keep in mind when we are looking for what is our hardness after the weld. Well, before answering that question, of course, depends, right? But depends on all these things. So if someone comes and say, what is going to be the hardness after I weld? It's like, well, you have to tell me first a bunch of things. So then I can tell you with some accuracy. I would say it's more or less this, right? But a hardness of a weld means nothing. If you ask that question, you're lost. You have to know which point are you looking for, which type of welding, which parameters are you aiming, and then you will have some sort of an approach. So I want to start like reading from right to left. So we are looking for this, for a hardness on a specific point. Why a specific point? Can someone tell me why in a specific point of your weld? You have a joint, you have a weld, and if I ask you, what is the hardness? Can you give me only one value? No, it's going to be a profile for sure. So specifying the point, specifying where you want to measure the hardness, it's really important. Usually it's assumed that we care about the maximum hardness, and the maximum hardness in carbon steels with normal processes are next to the fusion line. So that question is where, it's already answered if you're always asking the same, right? So where it's next in the what they call the coarse grain heat affected zone, or the zone that has more hardenability, that's where we will find the maximum hardness. But keep in mind that when they ask you hardness, when they ask you about hardness, you have to know what are you looking for and where are you looking for, right? So the hardness, what it depends on the hardness? Two basic things. How much martensite and other constituents do we have? And how hard is that martensite? And how hard are those constituents? I don't give too much attention of the other constituents, like vinylic phases or ferrite or perlite, because martensite plays a big role on the hardness. So basically when they teach you this for normal heat treatments, they will say, okay, after quenching, what you care about is how much martensite and how hard is the martensite. The rest is gonna be minor. But when it comes to welding, it's a complex heat treatment. So it's a rapid heat treatment. So we can apply the same kind of thinking, right? And think about, okay, my specific point, the hardness will depend on how much martensite and how hard is the martensite. So let's go with the easy one. How hard is the martensite? Can someone answer that question? Or what it depends? Don't read, because read and answer me.
Carbon content?
Exactly. Basically carbon content. People will argue, it's like, what other alloying elements say they have an influence, especially nitrogen, that behaves like carbon. But honestly, when we are talking about carbon steels, if you don't want to go too deep, carbon content. The martensite, as you will see in many of the models that we are going to go through, today we're going to go through only one, don't worry, and it's going to be short. But if you go and look into different models, you will see that the hardness of martensite depends mainly in carbon content. And it depends a lot. So it's not the same if we have like a 0.1% of carbon and 0.3, 0.2, or 0.5. That's going to change drastically. So that's something that you have to keep in mind. And actually, that's carbon content is the one that defines almost the carbon equivalent as well. So it's important. Carbon content, perfect. That's the hardness of martensite. Now, how much martensite we have? What are the main variables to say, okay, how much martensite I'm going to have after the welding in this specific point or region, right? Because exactly, cooling rate. And what is the cooling rate? Like what it depends? Yeah, the welding parameters, right? The heat input. Basically, that's something that Dr. Mena is going to teach in the future, but basically once you have the heat input, when you have the welding parameters, the thickness of your plate, you can have a good approach on your cooling rate. So that thing is basically done. You can have an estimate, right? Now, hardenability. And before I go on hardenability, this is the definition from the ASM, the American, right? I know, I don't want you to read. I just want you to highlight what is highlighted, that's the important thing. Hardenability is the ability of forming martensite under fixed cooling conditions. That's what you have to think about. Then the rest, it can be interpreted as however you want. But when people talk about hardenability, is how likely or how much martensite you're going to have after your cooling. But your cooling has to be fixed, because if not, they can start like going around. It's like, okay, what if I increase my cooling rate? Which one has more hardenability? No. When you are talking about hardenability, you are comparing two different steels, same cooling conditions. And with the same cooling conditions, one is going to have more martensite than another, and that's what it's going to give you that it's more hardenable or less hardenable, right? So you have to keep in mind, that's the definition. People, of course, this is one definition, and people use it as many other ways, but we cannot agree on some stupid things. This is one of them. So when we talk about hardenability, we need to know that the definition is that one, but people tend to use it in many other ways. But again, hardenability, you have to fix the cooling rates. That's the most important thing. And then how hardenable it is, how easy it is to make the steel more harder, or how easy to form martensite, they go next to each other. So if someone is like, no, hardenability has nothing to do with martensite, it has to do with the hardness of your materials, then yeah, but how do you achieve your hardness? Well, from a martensite sake. So the amount of martensite after your cooling, if you have your cooling rate defined, it's a variable of your hardenability, right? So going back to what Dr. Mendes taught in the last few slides, I know that it was the last few slides and we never pay attention to the last ones, but what are the main variables for hardenability? There are three things that you have to keep in mind when you want to know about hardenability of a steel. And this applies to welding and heat treatments. It's the same metallurgy, it's the same physical content. No, it has to do with how the austenite is at high temperatures. Because what hardenability means that your austenite is going to transform to martensite, right? So the austenite characteristics are the ones that are going to define how hardenable is your material, right? So what is the main variable you have in austenite? Chemical composition. We usually assume that all of our alloying elements are dissolved in our austenite, except for if we talk about like some really stable carbides like niobium carbides or vanadium or titanium nitrides, and they say, well, okay, they don't dissolve. That's true. But then we are going to see that those kind of elements, they play a little role in the predictions. But chemical composition of your austenite is one of the most important things. It's not the same if you have a 4140 or a 1040. And they have the same carbon content, right? But they don't have the same hardenability, no way. And that is because you have a lot more of alloying elements in solid solution in austenite prior your cooling and prior any transformation, okay? Of course, carbon content plays a role. So the higher carbon content you have, the higher hardenability as well, right? But you don't only have to look into carbon content when you care about hardenability. It's also crucial to look after the other alloying elements, right? Differently from hardness of your martensite. Hardness of your martensite is basically a function of carbon. I can give you that. But hardenability, no. And that's something you have to keep in mind, okay? Second, and this is what makes welding so interesting, austenite grain size. That is going to change your kinetics. It's not the same if you are cooling from 1400 Celsius next to fusion to 900 Celsius, right? And that's what makes welding so interesting, because along your heat affected zone, you have all the peak temperatures that you want. From 1400 Celsius, from close to the fusion line, all the way to your base material, you have different peak temperatures, right? Cooling rate might be really similar, as Dr. Mendes said, but the peak temperature is going to change. And when the peak temperature change, the grain size change. And when the grain size change, the hardenability change. So basically, what you have to keep in mind is like, for each point of your heat affected zone, you might need a new CCT, right? Of course, we are not going to do that. But that's something you have to keep in mind. It's like, each point of a heat affected zone is unique. And that's what makes a welding problem so complex, because when you're doing normal heat treatments, you just put the whole piece in the oven, you set up the temperature, you set up the time, and you have an austenite grain size defined for the whole piece. Then you're gonna have to start dealing with cooling rates. They might be different depending on the depth of your sample or piece, but the austenite grain size is more or less the same. In welding, no, and that's something that is also important to keep in mind when we are talking about welding. So, austenite grain size and chemical composition of your austenite, those are the most important things to define hardenability. And those are gonna define you how much martensite you're gonna have after your cooling, right? And as I say, the peak temperature will depend, the grain size is gonna depend on the peak temperature. And the peak temperature depends on where you're selecting your points. So we go back again. When I say it doesn't make sense to talk about only hardness, you need to specify a point. Well, that's the reason why. Because you can argue, yeah, we have the same cooling rate for the whole profile. That's true. But you don't have the same peak temperature, and that's gonna play a role, right? So this is all the variables in a nutshell of what you have to keep in mind when you're talking or when you want to predict hardness of a weld, okay? Now, most of the models that we are gonna learn or deal with, they're gonna assume that we care about the maximum hardness. So they're gonna assume that, okay, my peak temperature is 1400 Celsius. Never mind, and that's it. And then you can use those models for places or points in the heat affected zone that are not the maximum peak temperature, right? But again, the hardness depends on the peak temperature, and that will depend on where you are in the heat affected zone, okay? So, talking about hardness prediction, and this is like an overview. How can we estimate the hardness of your weld? If they come and say, like, okay, I need my maximum hardness in this steel plate with this process. You can go to the experimental, look at CCT diagrams. There are atlas, like complete books of different CCT diagrams for different alloying compositions. And usually they are divided into two big groups: heat treatment CCT diagrams and welding CCT diagrams. Can someone tell me the difference between those two? Why a normal CCT diagram? Why if I go to my colleague that he's a heat treatment guy, he works 24/7 doing heat treatments, I say, hey, do you have a CCT of this steel? Because I need to make a weld. And he gives it to me. Can I use it? Why?
Because in welding, the cooling rates are different from heat treatment?
Well, I can argue that the CCT diagram has the whole range of cooling rates. So I can say no. That the cooling rate, you can choose it. But there is something really important. Well, the process is a heat treatment. So exactly. The temperature. For a heat treatment, you don't want the austenite to grow. That's the whole point of making a good heat treatment. You say you heat it up to the minimum temperature you need, plus 50 Celsius if you want, and that's how you make a heat treatment. You don't go up to 1400 Celsius and then you cool down, because you're gonna have a more hardenable material, and that's something that you want to avoid, right? So normal heat treatments, depending on the alloy, they can be done 900 Celsius, 950, maybe 1000, but they're not gonna go up to 1300, 1400, right? So heat treatment CCT diagrams are usually what they call austenized at 950 or 1000 Celsius. On the other hand, welding CCT diagrams, they start from 1300 or 1400, right? And that's difference is the one that Dr. Mendez showed you in the last slide, where you have two CCT diagrams overlap and one is more move to the right to like lower times. That's what that we're dealing with. It's not the same, and we have to be aware of that, because we cannot grab any CCT diagram and say, oh yeah, I'm gonna predict your hardness is more around. If you use the wrong diagram, you can have problems. that you're not expecting. So experimental CCT diagrams, there are a lot. This is a German atlas that it's full of different chemical compositions. So you grab a chemical composition, then you have your welding parameters, you get a cooling rate, you go to the diagram, and you get a harness, right? The thing is, like, maybe you don't find the specific composition you're dealing with, or maybe you don't have access to these ones, because this guy is pretty expensive. I mean, if you're working in a company, you might get it, but they are really expensive for the personal use, right? So the other way we can predict hardness is doing compositional models, right? We have thermokinetic models that you can use in a software to actually predict the hardness, or even convolutional neural networks. Now that are like the trendy topic in any science. Artificial intelligence. You just feed the software with many data points, many of those CCT diagrams, experience CCT diagrams, and then you just like ask the software to a black box, what is going to be your hardness? Again, different ways. They are expensive. You need a good computer, or like you need to know what you're dealing with, right? So they are also an option, but I want to show you the ones that you can use on your spreadsheet, or you can use even when you have a pen and a calculator, because if you don't have a calculator, you're kind of screwed. But these guys, all these models that are empirical models, they're just simple equations that you just put in the chemical composition, your cooling rate, you make some few calculations, some steps, and you get to a value. That value, of course, is not going to be exact. It's going to be a good approach to the problem, but that's a starting point. So if you are off for many beakers, right, you know that you have to change something. If you're like on the edge, you can start doing some tryouts, but this is going to help you to move forward with the first approach. So what we're going to do now is like we're going to choose only one of these models. I'm going to choose the more basic and more easiest example that I can think of, and we're going to do the calculations, right? So you get used to on how these models work, right? So what we're going to choose is the Eurokia model. It's probably the one that Dr. Mendes showed you, or is going to show you, or he uploaded in the e-class. And this model is one of the easiest to use, and also the one that you can actually make sense of what they're doing, right? But nevertheless, they're all the same. They're all working the same way. So as long as you start like understand one model, then you can jump into many others, right? So what I have here is just a page of my CCT atlas, the German atlas that I told you, right? There is a copy at the UFA of the new edition, if someone is interested in seeing many CCT diagrams. But basically what you have is like a real CCT, that the ones like Dr. Mendes showed you in the class. And this is information from that CCT. Basically what it's showing out here is like how the mechanical properties change with the cooling rate. So if you look in this line, that's our hardness, and that's what we're thinking about. Of course, our hardness is completely related with the phases that we have at the end, right? With the amount of martensite and other constituents that we have. So these two are related. So what I want to do is like, okay, we're going to work with this example, and we're going to say, okay, from this case that you have a specific chemical composition, and I'm going to choose a specific cooling rate, we're going to make calculations. With a Eurokia model, right? We're going to input the cooling rate and the chemical composition. We're going to put it in our model, and we're going to have a value, right? So I include this image, which is basically what you get after you do Eurokia, that it's basically a diagram that says hardness against cooling rate, right? So if you see, it's more or less like having this. So you can back calculate your hardness versus cooling rate with Eurokia, right? And then you can actually see how good they match. But basically what you're doing is like, you're getting an equation for that curve, and then you're just putting your cooling rate, the one you choose, and you get a number. That's basically that's what it is. So again, I'm being repetitive, but this is what you have to put in your head. With the chemical composition, you have characteristic hardness value and characteristic cooling values. That means that with the chemical composition, you're gonna get point A and B. Point A is the point where you have all martensite, right? It's the time, the cooling rate, or TA5, whatever you wanna call it, for the maximum cooling time that you can have to have all martensite in your microstructure, yeah? And HM is going to be the hardness of that martensite. It's not going to depend on the cooling rate, so it's going to be a flat plateau, right? So that's your point A. So is someone lost? Are you following me with that? Yeah? On your point B, that depends on each model in particular, but what you have there is the time where you have no longer any martensite, and what is the hardness value of that, right? So with these 2 points, then Eureka, what he did is he fit an equation that is just a trigonometric equation to fit all his data, right? So he said, okay, I have these parameters, I have all this data, I just fit it with the equation I want, and he got an equation. And then with that equation, he grabbed the parameters that you can back calculate with different chemical compositions and get a hardness value, right? So what you have to do first is calculate those A and B points. Once you have those, you have basically almost all the problems solved, right? Once you have A and B, you have the characteristic hardness versus TA5 diagram. And then you go into with your TA5 of your interest, and you get a maximum hardness value, right? So, again, how we calculate B and A. You basically have those 4 equations in the left. Says tau M, tau B, HM, and HB. Tau is the T in capital letters here, and the H is the H there. So these 2 coordinates, you have them there, and depend on they're given by those equations, right? So what are those equations? What do they have inside? They have their equations that they depend on the carbon equivalent, again. So basically, the carbon equivalent is what is going to give you all the equation, right? So, but this is not as simple as one carbon equivalent. The authors, they define many carbon equivalents to use in many different equations. So basically, what I want to go is like those values, they depend on another set of functions that are above, that they depend on the chemical composition. So once you have the chemical composition, you can calculate those, and then you calculate these 2 points, and then with these 2 equations, you have your hardness. And that's what we're going to do. And after we do that, we are done. And it's not going to take us long, because I choose a carbon manganese steel. So we don't have to use all of those alloying elements. We only have to put the carbon and the manganese, and if we want it, no, just carbon and manganese, because the other ones, they are not in the equation, right? And we can calculate those. So I can do it, I can show you, but I need you to do it. So whoever has a calculator, I know, you come to class. Let's start calculating the first 3 equations there, so we can get like a sense of what are the values. So then we can go through, right? I can just like show you the results, but that's not how you learn to solve a problem, right? So any questions prior calculating that? You know what is CP? Yeah, you know what is CP because it says there 0.27, but you know what it means?
Well, specific heat capacity and constant pressure.
No, that's why I want to ask that, because it hasn't nothing to do with the CP from thermodynamics. CP, that's the carbon available. So it's more or less, if you see, in this case it's the same value as carbon, but when carbon gets to be like more than 0.3, is going to have another value that is closer to that. It's like the carbon content divided by 6 plus 0.70 or 27, something like that. But it's basically a function of the carbon. I didn't put it there because I didn't have the question, but you can go to the original paper or the information that Dr. Mena is going to give you, and you will find that. But can someone tell me the value of the first? I'm going to write it down here, because
what's the manganese content?
sorry, that's the chemical composition. That's how I write the chemical composition to not to be like too expensive. It's 0.27 carbon percent, 0.37 manganese, and then the rest. But the rest you can use it. You can use the 0.02 if you want, but it's not going to change anything, honestly. Again, you don't have to take this as like sharp, right? This is an approximation. So if we are off by 50 beakers, I'm gonna be happy at the end of the day, right? Because this is a first good approach, and the accuracy of this model depends a lot on the chemical composition range and the cooling time range. It's not the same if you want to fit for this side of the CCT or from like really, really short times. Maybe it fits better in a cooling range. So whenever, and this is a good piece of advice, whenever you're using these kind of models that are empirical, you have to be aware that they can throw you numbers that they have no sense, and you have to know that. You have to know what you're expecting. Hardness cannot be higher than martensite hardness, and hardness cannot be lower than your base material, right? Or more or less. So those kind of things, if you are by the end of these calculations, you get like 37 beakers, you know you're doing something wrong. Just don't write 37 beakers in your exam, because that shows you that you're just like monkey calculator, and that's not. So the first value.
0.3325.
Yeah, I have 0.344, but it's the same. I don't know how we have different numbers for the same case, but that's fine. It's on the order of 0.4 or 5. And let's go with 4 because I have all the calculations here, but it's the same. Again, if you're off by 0.01, nothing is going to change. My numbers might be wrong though. The second one?
0.34 again.
Yeah. And the third one?
0.373.
Yeah. I give you that. Right? So, something to keep in mind is that two things. See, right, like when it says like temperature and I put like 1350 Celsius, that's the sterilization temperature. So that's how we know that this is a welding CCT diagram, because nobody in their sane health will do a heat treatment with this sterilization temperature, right? So this has been done for welding. Yeah.
Do we know the delta H value?
Oh, that's a good question. Delta H value depends on the boron content, and that specific term is reserved for when steels have boron. The hardenability increases significantly, and the boron effect depends on the content of nitrogen, and a minimum amount of boron, like ppms of boron, can change hardenability drastically, right? In this case, you can omit that because we have no boron, but you will see, and this is not a coincidence, most of the Japanese authors that were treating steels in the 70s and 80s, they put a lot of attention in boron because there was the trending topic at that moment in that area, right? So boron steels, the people like Europe made a lot of work on boron steels, and they just include that term into the equation. But for this case, you can just forget about it. All right? So now we are good to calculate those A and B points, right? Yeah, those are the values that I have. And once we calculate those values, can someone tell me if they have a physical meaning? Or can someone tell me, okay, how can I check or like have a sense of if those values are like wrong or they're way off? What is tau m? Yeah, it's the maximum cooling rate that you can have, and you can have and you have to have all martensite, right? So basically, if you go to the CCT diagram, and if you have the cooling, you see the martensite, you need to know, okay, so my cooling rate, my tau, has to be in this zone, right? So it cannot be more than 2, or it cannot be 20. That's what I'm saying. If you're 20, you're off. Or your model doesn't work, or we made a mistake. But that's something you have to keep in mind, because those small checks, they're gonna save you 20 minutes in your exam. And I guarantee you that 20 minutes in your exam is like 2 hours in real life, or even more. So do those small checks. Check. If you get like maximum hardness of martensite, and you have this diagram, and your hardness is like 200 beakers, you know you're off, right? You know you're doing something wrong, and that's how you have to think in life. You don't know the answer exactly, but you know what you're expecting. So just try to see if those values, even if they're intermediate values, they approach to what you're expecting, right? So the same as tau b. Tau b should be the one that you don't get any martensite. So if you look, it's around 20 seconds there, but. Questions?
For the last equation, is it tan h and then everything else is
Yeah, this is the term. Yeah, there's some parentheses missing. Yeah, just the first one, that it's like 2.65 times the carbon equivalent number 3. Yeah.
For CE2 equation, is the C different than CP, or they're the same thing?
No, that's C. If not, it will be the same as, well, no, it wouldn't be the same as C1, but that's C.
So is it the same as the CP?
In this case, yes, because you are below 0.3 carbon percent. But if you're above that, C and CP, they changed a little bit. So again, one typo in these equations, and you're gonna get values that are completely off. So you will know if you're just like writing down the equations. It literally took me like 1 hour and a half to make all these calculations, and it's not because they're hard. It's because I have to rewrite them in Excel, and it was a nightmare.
Is tau m.31?
Yeah, does that make sense? Before I write it down, make sense or not? Are you okay with that? 0.3? Less than 1 second? Yeah? I'm pretty good with that, yeah. Everybody understand what it makes sense? That is less than 1 second? Who is not getting that, please raise your hand. Oh. And tau b?
21.
Does that make sense? Yeah? All right, let's move on. HM. Yeah, 516, or something like that. Yeah? Oh, what is the exact number?
527.
27?
Yeah.
Well, I'm gonna write. I'm just not giving you one, but I'm gonna write 516 because that's the number I have. But yeah, again, 10 beakers is the normal error you have in a harness. So that doesn't make sense to be picky on that kind of stuff. Now again, does it make sense? Yes. For rapid cooling rates, lower times, you have harness that is way off 470. So that makes sense. And this is what I was saying, right? The yellow lines, the time that you can have all martensite, it's around that value. And the green one, for all bainite, is around 20 seconds as well, right? And HB?
53.
153. Wow. That makes sense? I say so. If you see like 21 seconds here, I don't know why I put this one, but if you see 21 seconds here, it's like around that. It's like, I don't expect to be 153 exactly, but I just don't want this number to be higher than your martensite value. That's where you're wrong, or minus 20 beakers, right? But yeah, so now we have A, and we have B, right? So now it's just, we are like 2 equations away to get a number. Now, basically when you have A and B, you can input those values there, and you're gonna get your harness. First you have to get your X, that your X is then the variable in your last equation that is harness, maximum harness in your heat effective zone. And if you take a close look, X depends on what? What are those values? TM, TV are characteristic times, and your TA5 is your welding parameter, is your input. So we haven't used TA5 yet, but this is when it comes. Like this is when it's getting important, right? You use all the chemical composition, all information of your plate, that hopefully if you're making a weld, you know what you're welding, right? And you get all these values, A and B, with the coordinates T and H for each value. And then with the cooling rate that you can approximate with equations, or you can measure with your thermocouple, or you get those. All right? So, is someone doing the calculations? No. Questions? I know it seems like, looks like dumb, or like trying, or like there is no need of someone coming here to explain you how to use these equations. You will be surprised that it's not easy, and it's not straightforward to use them and to understand them. Once you understand one, and once you can use one, then the other ones, they are more like the same. But the way that you have to think, like when you're using these equations, is just not like if you have a spreadsheet that it's dumb-proof, yes, you just put your numbers there. But if you don't have your spreadsheet, or you have your spreadsheet and you're getting like strange numbers, you need to know where you can have problems, right? And this is why I'm taking so long for an example that is like with 2 different alloying elements. Yeah, please use these numbers. So,
How do we get T85?
oh, that's a good question. That comes in your welding parameter. That depends on your welding parameters, right? Because on your heat input. Nevertheless, most of these models, they also have equations for your T85 depending on your heating parameters. So if you go to the original paper, you will see that the first part, Eureka tells you, okay, if you have this current, this voltage, and your plate thickness is this size, then you're gonna see an equation that relates all those into a T85. You can also use the equations that Dr. Mann is gonna teach you in the next few classes. Yes? And you will know that.
Is this model for the fusion line?
Yes, this is giving you one hardness value. Yeah, that's a good question. And this hardness value, it's given for the
Fusion line?
is for the yes for the maximum hardness.
And are the values like average? Because I wouldn't expect even along the fusion line to have one hardness value.
Of course, this is
Like average
this.
values?
Well, this I wouldn't call it an average. This is these are a set of empirical equations that have been done with a lot of statistical data. So you have to account for the error of your statistical process and data to form those equations, and then the error for those equations itself. So I wouldn't call it an average, but it's a good starting point or a good approximation of what you're expecting on your hardness, in your hardness, right? But if you assume that along the fusion line you have all the same peak temperature and you have even distribution of alloying elements and your conditions are almost all the same and your cooling rate is the same, then you should expect the same things, right? Because you're seeing the same movie, same exact process. Yes?
Where do we, where on this graph can we find a T85?
No, this is the graph that you get. The TI5 is something that you have to use as an input. That's your input. Because you have chemical composition, you know what you're welding, you know the plate, you know the steel, but you also know the process. And with knowing the process, you have your TI5. Or you will be able to calculate your TI5 in the next 2 classes. When Dr. Mel starts talking about heat transfer, you will see that you will find these long equations from heat input and thickness plate. You will be able to calculate a TI5.
Then how do we calculate the X without T?
No, what? Sorry. I told you what TI5 to use. Sorry, 3 seconds. Because that's what I'm choosing, right? I'm assuming that my weld has a TI5 of 3 seconds. That's the input. Sorry, I thought you were asking me how to go to TI5. Yes, I could have changed this, right? And if you want, actually, you can use any TI5 you want, because up to this point, you haven't used your TI5. So you can go back to this diagram and say, oh, I don't want to try it at 3 seconds. I want to try it at 10 and see how good it fits. That's something you can, or you can do like any point you want. But that being said, you have the freedom of your TI5, but you don't have the freedom of the austenitization temperature. This is for the maximum hardness, right? So if they ask you, would this give me a good approximation of my hardness 1 millimeter away from the fusion line? You're saying no. Try it, but no. But if you ask me, okay, instead of having a TI5 of 3 seconds, I changed my welding, I changed my preheat, and now I have 20 seconds. Can I still use these equations? Yes, just change this. Right? Oh, I didn't give you a fucking number. There you go. See? So this value, it's something that relates to TI5. And once you put that value there, you get your hardness. And your approximate hardness is 300 beakers. Okay? I'm pretty happy with that. I'm pretty happy with how this equation works. I think to Eureka, right? But see, if you approximate 3 seconds in a logarithm scale, actually, so you will end up with something that is not off of your actual experimental data, right? So if you try let's say 20 or 10, you're gonna end up having another value. Now, a question. Do you expect a good fit or not for 40 seconds? If I ask you, well, you know what? My welding parameter is 40 seconds. Can you say something about that? Will you give me an answer and say, yeah, I just put my hands here? I give you this answer and I'm pretty sure it's...
Yeah, we can just change the T?
Yeah, you can. Would you be happy with the answer?
I think so.
I won't. And I'm gonna tell you what, kind of. You're fitting this model between A and B. Whatever is south of A and B, I don't trust. And you know that before, like for shorter times than A, hardness I can give you by heart. It's hardness of martensite. It doesn't change. Just grab the carbon content, make the calculation, you have the hardness. But for B, it's not that you can't use it, because it might fit in the values that are really close. But if you go way off,
You're saying because of the range of data?
yeah, because you fit that equation between A and B, between 0.3, between this time and this time. So if you say, okay, my TA5, it's 100 seconds, good luck with that. I know, I won't do it. So those are the things that you have to keep in mind. Those are the things that the paper doesn't tell you. Like, you read the paper and you're okay, and then you use like this model with this chemical composition and use 100. It's like, why I'm having like negative hardness value? And then it's like everything is all right, yeah, but you're just like, you have to know where your equation lands, right? And this is something very important as well with chemical composition. Each model has been designed for a range of chemical compositions. If you go to the actual paper, I didn't include the graph, but Dr. Mendes showed you a table with all the models and chemical composition. That's range. So if someone comes to you and say, you know what, I have this steel, and I have this welding parameter, and I have this TFI. Can you tell me about something about hardness? I say, yes. Just give me a second, give me your chemical composition. I'm gonna go to the table. I'm gonna see which of these models fits better for my range, and then use the model, right? Because we have so many available. We have more than 10 models that you can use. Different models that they look all the same. That's why I'm not going through all of them. Some of them they're kind of more tricky or have like more steps in between, but they're all the same. So as long as you know the time range you are fitting and the chemical composition you are fitting, these models, they should work pretty good because they are designed for that. They're back calculated from statistical data. So you expect to have but once you're off, you have to be critical with what you're getting, okay? Questions? That's it.